Okay, good afternoon. Today we will see chapter number 8, that is signal and systems analysis. Therefore, signal and system analysis means what? We have to do the in condition monitoring. We have to do the condition monitoring of the system. Therefore, condition monitoring implies determination of the condition of a machine or device or device and its change with time in order to determine its condition. In order to determine its condition at any given time. The condition of the machines may be determined by physical parameters like vibration, noise, temperature, oil contamination, wear debris, etc. A change in any of these parameters called signatures would thus indicate a change in the condition or health of the machine. If properly analyzed, this thus becomes a valuable tool to determine when the machine needs maintenance and in the prevention of machinery failures, which can be catastrophic and result in unscheduled breakdowns. The parameters mentioned above may be measured or monitored continuously at regular intervals depending on the application. It has been seen that a modest investment on instrumentation for measurement of these physical parameters would ultimately result in considerable savings due to the timely diagnosis of impending failures in plant machinery. In case of process machinery like pumps, turbines, compressors, etc., the rotating components are subjected to fatigue and wear, and maintenance problems are fairly acute, needing serious consideration. The situation is further aggravated due to the present day emphasis on large machines rather than a number of smaller machines with the same total output. Thus, in such cases, information regarding the parameters like vibration, noise, temperature, wear debris, corrosion initiation, and propagation of cracks and other faults, in addition to process parameters like pressure drop, flow, power, etc., which indicate the performance trend is useful. In addition, the relation between the possible faults and the monitored parameters has to be understood for meaningful use of the data compiled. Now, vibration and noise monitoring. Vibrations and noise signature of a machine are seen to be very much related to the health of a machine. Thus, measurement of vibration levels on bearing housing, relative movement between shaft and bearings, noise emitted by a machine, etc., can provide useful information regarding faults like unbalance, misalignment, lack of oil, wear, etc. Figure 16.1, for example, indicates the frequency spectrum of vibration velocity in a ball bearing in original new condition and also when the balls became defective. The increased level of vibrations and introduction of additional peaks is an indication of the defect. Therefore, you just see this is the original and afterwards this is the latter. The increased level of vibrations. When vibrations are introduced, then these are the additional peaks. Dotted line indicates additional peaks. Now, instrumentation for monitoring vibration and noise signals. In chapters 7 and 14, the instruments for measurement of vibrations and noise have already been discussed. In practice, piezoelectric accelerometers are commonly employed for vibration monitoring and microphones for noise monitoring. Frequency analysis instruments discussed in chapter 15 are also used for obtaining the frequency spectrum of the vibration or noise signals. Figure 16.2 shows a measuring and analysis system that may be used for monitoring the vibration signals from a number of machines. In case the data cannot be analyzed in the field, it may be recorded on a magnetic tape recorder and analyzed in the laboratory as shown in figure. Therefore, you just see here machine is there. Therefore, we have to measure the vibrations of the shaft. Therefore, here this shaft is supported in bearing. Therefore, we can mount accelerometer on the bearing to pick up the vibrations. Therefore, this accelerometer is mounted. Now it is connected to this channel. Then channel is connected to the FFT analyzer, and this we are getting here a record of the different or record of the vibration signals. And from the record of the vibration signals, we can see that whether the vibrations are under permissible limits or not, or whether there is a defect in the bearing, that we can judge. That is nothing but condition monitoring. See that this is the field measuring system, transducer, vibration meter, tape recorder. Transducer means accelerometer. Their piezoelectric crystal is there. When that piezoelectric crystal is compressed, at the time that electrical charge is produced, that is the characteristic of that piezoelectric crystal. And this is the typical records of vibrations of the machine. On y-axis amplitude, on x-axis frequency. This is recorded level. These are the limits. Now figure 16.4 and 16.5 shows a typical record of the frequency spectrum from one of the transducers. The peaks in the levels have to be identified and checked whether these are below the specified limits. The problem of identification of peak levels and specification of the limits has been discussed further. In figure 16.5, a system using a mini computer is shown for analysis and storage of data from a large number of machines. A real-time analyzer would give an instantaneous picture of the frequency spectrum. The levels of important frequency components present in the signals are stored in the computer and compared with permissible levels, data of which is available in the memory bank. In case any of the levels is exceeded, a control signal is sent to the machine concerned. The results can also be printed on a teletypewriter. Overall vibration levels may be indicated by a simple vibration meter, which would indicate the overall RMS levels for monitoring the frequency spectrum. The system shown in figure 16.6 may be used for manual operation, and the levels in the various frequency bands according to the filters chosen may be recorded. Therefore, this is use of mini computer for vibration signal analysis. See that the signals from machines are there. This is channel selector. Then that is fed back to this real-time analyzer. This is mini computer. This real-time analyzer is connected to the mini computer. And this mini computer is again it's connected to the machine control unit like this. The vibration monitoring by observer. See that machine is there, transducer. This vibration meter picks up the signal, then signals are filtered, then here recording is there on the computer and this observer is there. Principle of monitoring system, this is the normal level and this is the alarming level. Alarming level means what? Vibrations generated are more as compared to the usual vibrations or the permissible vibrations. Therefore, if that vibrations will exceeds that alarming level, then you have to change the bearing so that vibrations may be under control. Now this permanent monitoring system, see that this is the permanent monitoring system is there. It consists of input amplifier, filters are there to remove unwanted signals, filter 1, filter 2, filter 3, alarm, 3 alarms are there, level detectors. It may be minimum, it may be medium, it may be maximum, like that 3 categories may be there. Then automatic selection of signal, automatic selection of most dangerous levels. Then this vibration meter is there. The use of permanent vibration monitoring systems is necessary in applications like continuous process plants. The principle of such systems is indicated in 16.7. At a fixed number of frequency settings, the levels have to be monitored, and if they exceed beyond the alarm levels, an indication or warning is to be given. Figure 16.8 shows a permanent monitoring system based on the above principle. The center frequency for each filter is set according to the identified predominant frequency. An alarm is given if any level is exceeded. A desirable location for placing vibration transducers is on the bearing housing of any rotating machine. The vibration levels may be measured in radial and axial directions. In figure 16.10, the proper location of the transducer for measuring radial vibrations is at A, while that for axial vibrations at B. Locations A or B would not be proper locations, as the flexibility of the cover plates on which these transducers are mounted would affect transmitted vibration levels. A proximity transducer of AD current or capacitive or inductive type may be used for recording the motion of the shaft relative to the bearing. Two such units, H and V, as shown in figure 16.11, would give a picture of the motion of the shaft on an indicating oscilloscope. Position of accelerometer, see that this is the position of accelerometer. Accelerometer is usually kept over the bearing housing. A and B, it may be radial and axial. B indicates axial accelerometer to pick up vibration signals which are generated axially. A indicates the radial accelerometer. This is horizontal and vertical analysis of shaft motion. See that horizontal, one accelerometer is kept on vertical axis, one accelerometer is kept on horizontal axis. Next is wear behavior monitoring. Therefore, wear in machines can give an indication about the condition of a machine. For this purpose, the geometrical changes in the moving components may be monitored, and alternatively, the wear debris produced may be analyzed for size, loss rate, composition, shape, etc. Figure 16.14 shows a system for monitoring the piston ring condition in an engine or a compressor. The sensing is done by a proximity transducer. Any broken piston rings or those not in contact with the cylinder due to excessive wear can be easily detected. For analysis of wear debris generated due to relative motion in components like bearings, gears, seals, pistons, cams, etc., a number of methods are available. These include filters and chip detectors, ferrography, spectrometric analyzers, particle counters, etc. Therefore, this piston wear monitoring, this is the piston, this is the cylinder liners are there. Then this is the proximity transducer, filters and chip detectors. Machines with recirculatory systems can have filters to collect wear debris. Similarly, ferrous particles may be collected by magnetic plugs that collect ferrous chips From the shape of the particles, it may be possible to have an indication of what is going on in the machine. Figure 16.15 shows typical debris shapes. The debris from balls of ball bearings is of rounded rose petal type. From track is rounded with crisscross catches. From rollers of a rolling contact bearings, it is rectangular with parallel lines across the width, and from gear to debris is irregular in shape. The formation of spherical particles in large quantities indicates pitting of rolling elements and may lead to fatigue failure. Particle size, which is normally small, may become large at the onset of a fatigue failure. Thus, the origin of the particles and a possible onset of failure can indicate failure of a component. See that this is ball debris, this is track debris, these are gear to debris, and these are the roller debris. Next is spherography. This involves the separation of wear debris of ferrous type magnetically and arranging it in the order of size for examination. Figure 16.16 gives a direct reading ferrograph which can be used in the field. A sample of oil containing wear debris is diluted with a solvent which breaks down any gel which may be around the wear particles. The sample is fed to a transparent precipitator tube on either side of which are the poles of a magnet. The magnetic force attracting the particles is proportional to their size and magnetic susceptibility. Thus, the larger particles are deposited at the entry region of the tube, and the smaller particles and oxides of iron get deposited later along the tube. The amount of material deposited is measured by the attenuation of light from a light source placed below the tube as shown in figure. The light passing being detected by photoelectric transducers. The information about the condition of a machine is indicated by the distribution of particles along the tube, and thus the attenuation of light is measured at 2 points at a distance nearly 5 mm along the tube. Wear severity would be indicated by the difference between the optical densities at the 2 points. In normal rubbing wear, majority of particles are small. If the wear is severe, the number of bigger particles increases. In order to make a further detailed study of the wear debris, the debris are collected. See that this direct reading ferrography. This is oil inlet, oil drain. This is the magnet. Why this magnet is placed? Suppose iron particles are there in the oil, therefore these particles are getting attracted towards the magnet, and this pure oil will flow. Lamp is there. Then again this same case here, magnet is placed, ferrograph slide is there, so that a oil, if it is containing the any iron particle, that will be attracted by the magnet. In order to make a further detailed study of the wear debris, the debris is collected on a slide as shown in figure with a ferrographic analyzer. The oil containing wear debris is sorted by size down an inclined glass slide. The magnetic field gradient increases as the particles move downwards. The larger particles get deposited first. The slide is analyzed by an optical microscope which is arranged with the reflecting and transmitting modes of illumination. Red light is directed through the objective of the microscope. Opaque objects appear red. Green light is transmitted through the transparent objects which appear green. Other objects appear in various shades of yellow-green. This helps in distinguishing metallic from oxide particles. Further, a heating of the slide to 333 degrees Celsius or so turns low carbon and alloy steels to temper blue color, cast cast iron to light brown color, and bronze to dark brown, chromium and aluminum remaining bright white colors. Thus, particle identification is also possible. Next is spectrometric analyzers. Oil samples containing wear debris are taken from the sump and analyzed by any of the following methods. First is atomic absorption spectrometer and second is emission spectrometer. The technique is called spectrometric oil analysis program, SOAP. Figure 16.18 shows an atomic absorption spectrometer which is based on the principle that every atom absorbs only light of its own specific wavelength. From the combustion of the oil sample, the metallic elements are atomized. In a light beam passing through the flame, certain wavelengths get extinguished due to absorption by the free atoms of the metals. Since each element has its characteristic wavelength, it is possible to measure the amount of light absorbed and indicate the concentration of an element in ppm, parts per million. In figure 16.18, a chopper is used to produce an AC signal for the detector. The monochromator is turned to accept light of a certain wavelength. A meter indicates the difference between the light emitted by the light source and that received by the monochromator. The procedure has to be repeated for each element to be detected. Therefore, this is atomic absorption analyzer. You just see here, this is light source, this is chopper, then this is the sample, this is monochromator, photo detector, amplifier, readout, and emission spectrometer with which it is possible to analyze simultaneously a number of elements. A rotating graphite disc carries the oil to be subjected to high voltage excitation. A spark excites the various metallic elements after which they emit their characteristic wavelengths, the intensity of which is measured by various detectors. Therefore, this is emission analyzer. This is particle counter. Therefore, several elements can be analyzed using this method. These include copper, iron, chromium, nickel, lead, sodium, aluminum, magnesium, silicon, and silver. With a knowledge of the composition of each machine element, it is possible to identify the parts wearing out first. Particle counters. The size, distribution, and concentration of wear particles in oil can be determined by various types of particle counters that have been developed. Figure 16.20 shows one such particle counter, which is based on the light blockage principle. The oil is passed through a sensor consisting of a light source and a photodiode. A particle passing through the window blocks light proportional to its axis. Accordingly, an electrical signal from the photodiode is sent to the counter. Thus, counting and sizing of particles is possible. The turbulent flow in the narrow tube results in rotation of the particles. This is helpful in that the largest cross section is likely to face the detector at least once before leaving. A vacuum pump is used to suck the oil from its container through the device. Concentration levels in several ranges of particle sizes are displayed. Therefore, this is the end of the chapter and end of the syllabus. Now, from tomorrow onwards, I will take objective questions. That is, we'll study objective questions. Thank you very much. Thank you.